So we saw that one pi vertex in momentum space has the following form: E number of external lines, P1 to PE, has a loop expansion if lambda m or only if lambda, L comma n, P comma n, where I, L comma n is integral j equals 1 to L dLj, then product over k equals 1 to n, sum over j akj lj plus sum over I dki pi square plus m square minus I epsilon to the power minus 1, where L is the number of loops, LJs are the loop momenta, and n is the number of internal lines. And we want to study divergence structure of this of I. And to do that, we introduced Feynman parameterization. So study divergence structure of I Ln introduced Feynman parameterization. This is what we had done in the previous lecture. So let us use that Feynman parameterization in this particular integral. So Feynman parameterize I L comma n. So the way to identify this as this factor this is supposed to be identified with 1 over a1 to an, where ak is given by sum over j akj lj sum over I bki pi square plus m square minus I epsilon. And if you identify that way, then I L comma n will be like this. That is how it looks like. Now, leaving aside this portion, gamma times this alpha integral, we are basically having to do an integral over the momenta of this quantity. Okay, so that's where the crux of the matter is, and that integration has to be done by an analytic continuation. We have this I epsilon prescription. So we will do analytic continuation. For that purpose, you write this this entire thing, this portion. Let us focus only on this portion. Let us write it, expand it in the following manner. So there's a sum over k, but each term here for a particular value of k is a square of a 4 vector. That 4 vector is a linear combination of L's and P's. So I have broken down that 4 vector in the norm square of 4 vector as minus temporal component square plus 3-dimensional component square, 3 vector square. And then I can write it as the entire thing as q0 square minus q0 square plus q vector square, where of course q vector part is this one and q0 part is this one. Okay, it's a k goes from 1 to n. So there are n, so basically you are summing over n such vector norm square of n vectors with certain coefficients alpha k, and so you end up getting, so this can be interpreted also as a norm of a 4 vector. Okay, so this means that I L comma n is equal to gamma n times and of course q is a linear, q is obtained by a linear transformation on L's, right? So this is the relation between Q and L. So it's a linear. And therefore, if you had written down this measure in terms of the Q integral, that would pick up a Jacobian, which is constant, and that Q integral will have to be performed where this will have pole, right? This is a minus n, so this downstairs, and there will be a pole. So what are the poles? Poles will be at Q0 square is equals Q vector square plus m square minus I epsilon. And that gives you Q0 equal to plus minus omega Q vector minus I epsilon tilde, where epsilon tilde and epsilon, I mean epsilon tilde is linear in epsilon and have the same sign. Usually it is not called epsilon tilde, it is again called epsilon. And this omega Q vector is square root Q vector square plus m square. So in the Q0, if you want to perform the Q0 integral, then in the Q0 plane, complex plane, so this is the analytic continuation. Q0 is a real number. Now you look at it as a complex number, and this integral over Q0 will be on the real line here. That is the real line. And there are poles, Q0 equal to omega Q minus I epsilon tilde, which is, if this is omega Q, then the pole will be here, and minus omega Q plus I epsilon tilde, which is here. Okay, so this is omega Q, this is minus omega Q. Now, as a complex integral, whichever way, so you can deform a contour. So this is like a contour. This is a line along which you are doing the integration, and you can deform a line as long as you do not hit a singularity, a pole, right? A singularity. So that means you can deform this line. You can by an angle theta. You can rotate it by an angle theta, and if you use the complex contour integral method, the result will not change. So this basically what you are doing is that you are defining a new Q bar 0, which is analytically continued version of Q0, which is this rotation e to the power I theta, and as a result you have L bar 0. Q0 is basically constituted out of L and P's, so L bar 0 is e to the power I theta times L 0, and P bar 0 is e to the power I theta times P 0. Okay. So the analytic continuation will be given by Okay. And for any value of theta is allowed as long as this line does not hit singularity. You couldn't take theta in this direction, then the line will hit the singularity. If you had rotated in this direction, that would be a wrong direction to go because it will hit singularity. You are going this way. So we will choose theta equal to pi by 2, which is basically a Euclideanization of this momentum. Theta equal to pi by 2 is just a factor of r, factor of I. That's an Euclid. So Q bar, L bar, and P bar are the Euclidean momenta.